Hello. Well, I'm planning to show you some computer-generated pictures of the trajectories of this system that I just solved in the previous mini-lecture. I remind you this is problem 3 on that WeBWorK set. Okay, so you might remember that we had this, the xtt is ax, and the eigenvalues of a were plus or minus I, pure imaginary, and we found that solution. We didn't get the picture. We didn't draw the picture. Okay, so we found this solution here. And one of the things I want you to notice about this solution is that both of these functions are 2 pi periodic, right? In fact, they're both solutions to the second order ODE if the roots of the characteristic equation are R equals plus or minus I. You notice here the eigenvalues of the matrix are lambda equals plus or minus I. There's obviously a connection between those. All right. The solutions here are ellipses in the x1, x2 plane. Okay, that's not so easy to see, but it is easy to see that they're periodic, right? If I add 2 pi to t, I get the same x, and the same x1 and the same x2. Okay, so I'm going to put this on the computer. If I let x be x and y, then I can, these are the variables that we can use on the computer, and you get dx dt, the scalar, is minus 1 times x plus 1 times y, and dy dt is minus 2 times x plus 1 times y, right, using the matrix multiplication. So let's go to our app and see that. Okay, oh, but before we do, there's something I want to talk a little bit about, and that is the trajectories in general if the eigenvalues of the matrix are complex A plus or minus IB. So for in general, right, if we think about e to the lambda t v, and we'll call it v1, right, that's going to be e to the a plus ib t v1. So lambda 1 is a plus ib. And if I remember, the real and imaginary parts of this vector valued function, complex vector, are the two solutions. This is e to the at times e to the ibt v1. And then this is e to the at times cos bt plus I sine of bt, all times this vector. Okay? So this thing is either growing exponential, it's constant, if a equals 0, e to the 0 t is just 1, and it's a decaying exponential, well, let's just say decaying, if a negative. And then this part here is always periodic, and the period is 2 pi over b. Cos bt and sine bt are periodic with period 2 pi over b. So I put them together, and if a is 0, this is periodic, and in fact, it's going to be an ellipse, or maybe a circle, which is a special case of an ellipse. But if a is positive, it's going to go, this part's going to go around, but I'm going to be multiplying it by a growing factor. So it starts out, and it just starts, it starts spiraling out. So I get trajectories look like this, or trajectories look like this, ellipses, or trajectories that decay, they come in the A negative. Okay. So actually, your WeBWorK problem asks if the trajectories are spiraling out clockwise or ellipses going clockwise or counterclockwise and all that. We haven't really answered if it's going clockwise or counterclockwise. This A is all you need to determine if you have spiraling out, ellipses, or spiraling in. Now to figure out which direction it goes, that can be that's fairly easy by just plugging in one point. To figure out if it goes counterclockwise or clockwise, consider this, dx dt, when x is 1, 0. For our example here, minus 1, 1, minus 2, 1, 1, 0. That picks out the first column. So that means that in the plane here, here's the plane, it's going to be spiraling out or in. Here's x1, and here's x2, or in our computer program, that'll be x and y. And if I'm over here at the point 1, 0, the velocity vector is -1, -2, right? The velocity vector is pointing down and to the left, more down and to the left, a little bit to the left and a lot down. So the only thing it can be doing is it's going clockwise. So the ellipse moves, well, the ellipse doesn't really move. Trajectory goes clockwise around an ellipse. And clockwise is just from that picture. It's going to be going around. It's got to go around, right? Because it goes around the center. Okay. So and it's around an ellipse. So the trajectory moves clockwise on an ellipse. So let's go now to the picture. All right, we'll share the screen here. Okay. All right, here's our website. Let's make it big. Okay, got 2 copies of the website. Let's go to this slope field applet. Here's our slope field applet that we like. We're going to go to system and do this system we talked about. What is it? Dx dt is minus x plus y. dy dt is minus 2x plus y. Okay, there we go. There it is. And you can kind of see a swirlingness in the clockwise direction here. So let's put in the initial point, -3 and -1. And when I start this, I expect it to go on an ellipse in the clockwise direction. Well, it left the screen. So let's zoom out a bit. Let's go from double this window. Go from -8 to 8. Oops, -8 to 8, and minus. Actually, let's clear the curve while we're doing this. -6 to 6. Okay, so now we zoomed out. We're going to still start at that point, -3, -1. Oops, I expected an ellipse, but it didn't get one. It spiraled out. So hopefully we've done this enough that you remember that that's because Euler's method is lame. If we do Runge cut of 4, we indeed get to the accuracy here that we're on an ellipse. So there's the trajectory. So one of the things to notice about this is that there are no directions where the arrows are pointing straight into or straight out of, or straight to the origin or straight away from the origin, right? Remember that was a condition for an eigenvector with a real eigenvalue. You have a real eigenvalue, and if the vector points straight towards the origin, and that's a negative eigenvalue, or straight away from the origin, it's a positive eigenvalue. Here, there are no directions where the vector is straight in or straight out. There are no real eigenvalues. In some weird complex land, yes, it's AX is equal to, AV is equal to lambda V, but the lambda is complex, the V is complex. We're not really in the two-dimensional plane anymore. I got a few pictures of the vector fields here. Let's see, I think I might have to. Pure imaginary eigenvalue. All right. This is in fact the vector field for the same A that we've been talking about, -1, 1, -2, 1. And since the arrows have different lengths, it's a little bit hard to see, unlike the other picture, but even over here, the direction is not towards or away from the origin. There's no directions in the real plane, the x1, x2 plane, where AV is equal to a scalar multiple, a real multiple of V. Okay, let's look at a few examples with, here's a complex eigenvalue. Here the eigenvalue is 1 plus 2i. Here's an example where, according to my rule, A is 1 and B is 2. So e to the at is a growing exponential. So that's why you get the spiraling out. In fact, maybe we should go to the other thing. I think we can remember this. 1, 2, minus 2, 1. Go to the slope field. 1 times x plus 2 times y, negative 2 times x plus y. I think it's there. Okay. Yes, here we do get a spiraling out. If I start really near the origin, it spirals out. Okay, cool.